Welcome to yet another class, another week where we gather here on YouTube to provide you with these practical and theoretical insights that will assist you on your journey towards becoming a skilled climate technician. In other words, acquiring the skills to repair any electronic circuit board within the climate control sector. Today, we will discuss the E6 error associated with TCL, the TCL brand. It's a brand that I have not frequently mentioned in my lectures, isn't it? It is a newer brand, so it will appear a bit more over time. So, error E6 on TCL. Let's understand what it is and what to do. TCL error E6. Although your brain is almost failing already. TCL error E6. Error E6 on TCL. TCL error E6. Error E6 on TCL. The first question you ask is, what does the error mean? Don't bring the error to me. The error's on the machine, dude. I don't know, man. To get ready for this lesson, I'll look up what the E6 error was before. I have observed that the E6 error code in TCL systems is typically associated with the evaporator fan. Once again, the TCL error is connected to a malfunction in the evaporator motor fan. Motor fan. When I hear that, when you hear that, what are you going to think? What are you going to analyze? What are you going to seek to analyze? When you hear this, you'll think the defect might be in the evaporator, obviously. It could potentially be the fan activation mechanism or the fan feedback system. Fan activation mechanism or fan feedback system. The initial action you can take is to replace the fan. I didn't ask for someone to buy it for you to replace. But if you have a fan, you go there and replace it. A test one. Let's conduct a more detailed analysis here that you are capable of performing on this board. What actions can you undertake? Initially, does the fan rotate properly? If it doesn't spin, if the evaporator fan doesn't spin, the issue is either with the fan or the control circuit. Okay? It's either the fan or control circuit. Check the terminal block for voltage to run the motor. If there is no voltage for the motor to turn, the problem is with the drive. If there is voltage for the motor to turn, the problem is with the fan. See the logic. Only focus on the error. Only focus on the error. Error E6 on the TCL. Fan. Check the machine's behavior. The fan turns on. Alright, if it turns on, it could be... First, if it doesn't turn on, doesn't rotate, the issue might be with the fan, the turbine, the motor, or the small fan motor. Might be the motor. It is not rotating. Alternatively, it might be the signal that is supposed to arrive for it to activate, for it to rotate. It could be the signal that is intended to arrive but is not arriving. If the electrical voltage does not reach it to make it rotate, it will not spin. So what should you do? You take your multimeter, adjust it to the AC voltage scale, and then measure the voltage at the fan connector. All right? You will measure the voltage at the fan connector. Then, with the voltage measured at the fan connector, if there is no voltage, there is no voltage. The fault is in the activation circuit. If there's voltage and the motor's not spinning, the fault's in the motor. Could it be the capacitor? It could be the capacitor. It's the first thing you will check, the easiest thing to fix. It's the fan starting capacitor. If it's black, usually you'll check if it's the TCL case. I'll focus on TCL, okay? It's not an error or a generic analysis. It's an analysis of TCL and E6. Obviously, I like to think about the effects in a generic way because it will be useful for other machines. So this logic I'm creating for you is for all types of BLDC motors. Follow this line of reasoning. Pay attention to the line of reasoning, okay? So if mine is spinning, how are you going to think? I haven't even touched the board yet. I'm considering the defect. If it is indeed rotating, then the drive circuit appears to be functioning correctly and the motor seems to be in good condition, particularly the power component of the motor. Evidently, the power section seems to be satisfactory. If it rotates, then stops and gives an error, it's because the board is not seeing the rotation signal. It's not seeing it because either the motor is not sending the signal through the feedback connector, which is this smaller one here, or the motor is not sending the rotation signal back, or there's a defect in the board and the signal is not reaching the microcontroller. There is a caveat with this type of circuit, which is the AC voltage reading circuit. In evaporator boards, many of them, let's say all of them, because I haven't analyzed every single one to be absolutely certain. However, the majority of them will possess an AC voltage reading circuit designed to interpret the AC voltage signal. If this particular signal is faulty or inadequate, the board will not proceed to activate the fan motor. In the initial analysis, right, returning to the first analysis, if it doesn't activate and everything's fine with the activation circuit and motor, how will you know? I will explain how you can tell. If everything is fine, then the problem might be with the AC voltage reading. If the board doesn't read the voltage, it won't speed up or activate the fan. And it'll show a fan error, usually not for reading accelerated voltage, rarely, okay? So it's in parentheses because it's a defect that happens, but if the motor turns, it stops. And if it turns and accelerates too much, you will see this behavior. It accelerates a lot, then it cuts off. It's because it isn't getting feedback. There's no return signal. All right, okay. So here on the bench, see, here's the board. The little face of TCL here, look. Here it is, the little face of it, condenser, evaporator, the anti-nasal circuit in the evaporator. I'm going to disconnect the motor, okay? Without the motor. I want to analyze the display here, move the display over here. It's better for you to see. I'm going to power it up here, powered up. I'll show here, 16 degrees right, not leaving without compressor. I don't want the compressor to fail on the evaporator. Here it's without the fan connected, just to see if it will give the error. Just confirm if it will give the error, okay? If it takes a bit longer, please observe it is currently set to 6. Do you see it? It is indeed 6. So let's proceed to turn off the bench here. Notice the error code is 6. All right, the error code is indeed 6. So I will proceed to turn it off and connect the fan. I'll connect only the power section of the fan, just the power section, and I'll apply some electrical tape there just so you can observe the fan's rotation. Everything good. I've connected it. So let's proceed to turn it on. Turn it on, 16V battery again. Now the fan will turn on, but it's without the feedback signal. I just connected the fan here, it will rotate. I would like you to observe that it will maintain a high rotational speed. It will not decrease its rotation because it typically oscillates. It continues to modulate its speed. It's on. It goes to a high rotation. Can't see it well, right? In the video. Set it to high speed. It's not modulating. It's not decreasing. It cut off now. It cut off. It has altered once more. Short circuit has occurred once again. Now let's carefully observe it modulating. I will proceed to connect the fan here to the feedback connector, and we shall witness it modulating now. 16. I will measure the voltages for you to observe. All right? I will measure it right now, in fact. Now I shall measure the voltages. I will remove the display here. I shall proceed to measure the voltages here at the evaporator unit. This way, we can observe the values that ought to be present at the pins corresponding to the fan. Alternating current voltage. At the fan connection pins, it's rotating correct. From the red wire to the white wire, it is providing 55 volts of alternating current. From the white to the black wire, it reads 51 volts, and from the red to the black, it reads 33 volts. Notice the voltage is low. It's not meant to be 220 volts. The modulation is slow, and I'm not sure if you can see it's running slower now. This is due to receiving feedback. If I remove the feedback now, let me check if it causes an error. I'll remove it here so you can see if it speeds up. I took it out. Observe, it accelerated to 150, 180, 200. The velocity heightened, notice. 220, observe. Magnificent, isn't it? What is this? The power of feedback. The feedback, when I took it away, he sped up to get the feedback. Now I'm going to give the feedback back to him. Observe here, please. I have returned the feedback to him. He has already, as you can see, adjusted the speed accordingly. Notice. It decreased progressively to approximately 57 or 58. Observe attentively. It has already been adjusted because now there is feedback to reduce the voltage being provided to the fan. Let's proceed to measure the signal at this moment. The 3-pin signal, specifically pins 1, 2, and 3, correct? And what exactly does it contain? It is oriented from the bottom to the top, taking into account here 3 pins, correct? Pins 1, 2, and 3. The first from the bottom is not VCC, apologies, it's GND. The middle one is ALT, and the top one is VCC. So it's GND in the middle output, actually the input signal, and there is the VCC. VCC is the 5 volts. Let me measure the voltage here. AC, no DC, correct? At this moment, the DC voltage present here within the feedback loop is anticipated to yield a voltage measurement of precisely 5 volts. Observe, it is indeed 5 volts. I'll turn it here. Here you have the 5 volts, exactly 5 volts. Kindly remove the tip. There are 3 pins available. From here to there, I provide 5 volts. Now I'll take from here. Keep 0 volts here. I'll take the middle pin. How much voltage is on the middle pin when the machine is rotating? 2.2. Hi. 2.3. At the current speed, if you accelerate, it'll change, but usually it's usually if it's 5 volts, it's 2.5, 2.3, this one's correct. If the master here is at 5 volts, it'll cause a sensor failure. An additional test that you have the option to perform is as follows. I shall energize it and then I will disconnect the connector located here. On the board over there, you will energize and subsequently deactivate the control, leaving it solely energized. Okay, look, I energized it. It stayed at 5V, which is the signal pin for the feedback. If I rotate it with my hand, it zeroes out. A bit more, it transmits a 4.6 volt signal. Subsequently, it resets and then transmits 4.6 volts once more. If I rotate the motor, the signal fluctuates. It means the feedback is signaling. The feedback connector is exclusively connected. I am linking the ground pin to the output voltage pin, which functions as the signal pin, and I am manually rotating the motor to check if it oscillates between 0 and a higher voltage. It is indeed oscillating here between 0 and a higher voltage up to the maximum voltage and power supply, which in this specific instance is 5 volts, correct? Consequently, it should oscillate between 0 and 5 volts. If the fan's power supply is 12 volts, it ought to oscillate between 0 and 12 volts. Allow me to switch this off. This component here, this small black one, contains pins numbered 1 through 7. Pins 2 and 3 are the activation pins. What precisely am I expected to do in this particular situation? When you have a machine of this kind, where the motor is not currently in motion, you will need to exert force to make the motor rotate. How will I do that, Lawhander? Let me explain. You will utilize an analog multimeter to compel the motor's rotation, correct? In order to activate the motor. You saw that when it turns on, the analog multimeter is set to X1. You notice that when it turns on, it takes a little while to start the fan, right? This delay, I will force the start right here. So it turns on before sending the signal to the fan, and it will start at maximum speed. It'll start at max speed since I'll activate it directly. Simply connect the fan at this point, correct, and then disconnect it and reconnect the fan. Observe the fan's capacitor, this small blue component here. It is rated at 1.5 microfarads, and if it displays a value of 1.3 or 1.2, it is already low and requires replacement. If it decreases by merely 0.1 or 0.2, but 0.2 from a 1.5 microfarad capacitor, then it has decreased significantly, correct? All right, let's proceed. I'll energize the system. I've energized it and we'll activate it directly at this point. Observe, I've activated it directly and notice how it rotates. It's already activating directly. I'll disconnect it here as the board hasn't even issued the command yet. I'll send it now. The board hasn't even issued it yet. I'll proceed to activate it directly, activating it directly here on this integrated circuit that I know is responsible for activating the fan. If I conduct this test and ascertain that the fan hasn't initiated yet, oh, it has started now. Let me switch it on here. I understand that the fan isn't starting, and I want to determine if it's the fan itself or the activation circuit. To discern what is activating in this component when I activate this component here, I'll obviously analyze its data sheet or the circuit traces to comprehend its function. It's an optotriac, this small black component here, which will send a signal to the fan to initiate. If I activate it and the motor turns, then the motor is functioning properly. The power circuit is operational, which we refer to as the hot circuit. However, the cold section, which is the low voltage section, is malfunctioning. Either the circuit is faulty, it's not coming from the microcontroller, or remember the AC voltage reading? Or is the AC voltage reading circuit having a problem? In the case of this board here, the AC voltage reading is probably through these larger resistors here. Most likely. For the fan, I reduce the voltage level. If I activate it with the analog multimedia and the motor starts working again, the motor is fine, the activation circuit is fine. I'll check from here to the microcontroller. If there's an open trace, an oxidized capacitor, something might be disrupting the system. Is everything okay? The micro should be sending, but it isn't. What will the person think then? It's the microcontroller. At this juncture, you'll recall that there exists a current measurement circuit or an AC voltage measurement, which on this particular board are represented by these two resistors here. You will check if these resistors have changed, if they are open, if their trace is reaching the microcontroller properly, all according to standard. And if it sends the signal and it's not sending the correct signal, you will check the connector circuit. You are already knowledgeable about whether the fan signal is functioning by simply powering the machine and manually rotating it while measuring the voltage at the pin. If the voltage at the pin changes, you are aware that the motor is faulty. If it does not change, the motor is indeed faulty, correct? If it changes, the motor is operating correctly. But even if there's a rotational error where the motor accelerates excessively and triggers error 6, you will suspect the circuit. Here there are some small diodes. Look at this little circuit. This small circuit from the connector. There's a little diode kind of like this. There are some resistors. You'll follow the path, analyze everything. The path is okay and all. All right, folks. It's that simple. It's that simple. TCL Air Conditioner. Cool? Is it clear? Thanks. We're in this together. God bless you. Sending a big hug. I'm heading out now. Goodbye. Goodbye.